In this week's first lecture, I'm going to solve 5 exercises at the end of chapter 9. And in the second lecture that I will post on Thursday, I will post a couple of exercises at the end of chapter 10. So this week it will be all some exercises from the end of chapters of 9 and 10. I'm not going to start the new chapter 11, which is least square linear regression. All right, so the exercises that I'm going to be solving today at the end of chapter 9 are 9.4, 9.5, 9.7, 16, and 17. So let's start with the first one, 9.4. So this is an exercise for estimation a parameter of a distribution by either method of moments or the maximum likelihood method. So we can choose either one of the methods that are available, and I'm going to show the solution by using both of them. So we have a sample of 3 observations, x1, x2, and x3. And we know that it's collected from a continuous distribution with this density. All right, the distribution has only one parameter, theta, and it's defined between 0. The distribution is defined between 0 and 1. It's 0 all elsewhere, so it's non-zero between 0 and 1. So for x between 0 and 1, the distribution is theta x to the theta minus 1. So this based on this parameter, we may have a different shape of a function. So this is the shape defining parameter of our function, which we do not know right now. So based on these observations, based on these 3 observations, we are going to make our estimate for what theta can be. All right, the method of moments works like this. We can either use the central moments or directly the moments, the population moments, and we're going to equate them with the sample moments that we collect. We can just, since there is only one unknown here, theta, we can use the first population moment, mu1, and which is actually expected value of x. So mu1 is the expected value of x, and the sample moment m1 is just the average of these sample observations. So we start like this. We have the density, which is theta x to the theta minus 1 given in the question. And so this first paragraph actually just repeats what the question is about. All right. And I will also post this PDF that is available here on Oticlass and on Co. So you will have a high resolution version of this PDF as well. Although the video may be low resolution, you can, while listening to this video, you may also open the high resolution PDF that I will share with you. Now, we have one unknown, which is theta. And with the method of moments, we may use, as I said, the population first moment, which is m1, which is the expected value of x. If you remember the population moments, the expected value of x is the first population moment, expected value of x squared is the second population moment, and so on. And based on the number of variables, unknowns we have in the distribution, we may use 1, 2, or 3 moments and just equate them to sample moments and solve a sequence, a series of equations with a certain number of unknowns. So m1, the population moment, when we try to find that, it's defined as, if the definition of expected value of x is x times the PDF of the probability density function of x, and we integrate it from 0 to 1. So when we do that, it becomes x times theta x to the theta minus 1. So x multiplied by this, it will be 1 plus theta minus 1. This minus 1 is going to go. So it's going to be the integral of this entity, which is theta x to the power theta dx. So theta is a constant here. It can be taken out of the integral. And when we integrate this, it becomes x to the power theta plus 1 divided by theta plus 1. So this becomes the integral from 0 to 1. When we have this definite integral, when we give 1 to x, it's going to be 1 over, so this is going to be 1 here, which will be theta divided by theta plus 1. And when you give 0 to x, this one will be 0, so everything is going to be 0. So the result of this integral will be just the first term, which when we equate to which we get when we equate x to 1, which is equal to theta divided by theta plus 1. As you can see, the first moment itself does not contain any x terms or anything. It's the first moment is an equation which contains the population parameter. Whatever the population parameter is, it's theta divided by theta plus 1 is the first population moment of this. Now, what we are going to do is we're going to equate this to the sample moment. This first sample moment is just defined as x bar, the average of these 3 sample observations. When we take their average, we add them up, divide by 3, we get 2.3. So simply 2.3 is equal to, when we equate these two things together, 2.3 is equal to theta divided by theta plus 1. Simply theta hat becomes 2. So with method of moments, our estimate for theta with this sample is 2. All right, so this is how we estimate it by method of moments. So now let's try maximum likelihood as an alternative. We could have found, we could have made the same estimate for theta hat by using another method, maximum likelihood. For that, we need to first write out what is the probability of observing the sampling units, the observations. There are 2 D's here. All right, that's a typo. So the joint probability of observing these things is just the we are going to multiply these at this xi observations at these observed units. So if you remember what we were talking about, this even in continuous, although this is a continuous distribution, if we just say the probability of observing x at this particular unit is 0, we know that. But even if we just compute the probability within a certain interval, we see that it's proportional to this PDF function. So although this is not the probability of observing the sampling units is not equal to this exactly at this points, because point probabilities in continuous densities are 0. But what we can say is the probability of observing the sampling unit is proportional to this product here. Okay, we can say it's proportional. And which means that if you want to maximize this thing, if you maximize this, we actually also maximize the probability, the actual probabilities as well. So another thing is, instead of maximizing this, we can also maximize the logarithm of this thing, because logarithm is also an increasing function like this. They will be, if you maximize the logarithm of this, you will be maximizing this as well. So in order to turn this product into summation, we take the logarithm of this equation here. When you take the logarithm, the multiplications becomes turned into summations. So it becomes logarithm, natural logarithm of theta plus, when you take the logarithm of this, it will be theta minus 1 ln x. So this power will be a multiplicative term here, and that's the logarithm of individual xi's. Everything is a summation here. So if you look at this term, it will simply be, we add this 3 times ln theta. This is constant. It doesn't depend on what xi's are. So 3 ln theta plus theta minus 1. This is a constant in terms of xi as well. So we can take this out from 1 to 3 ln xi. So we have this. Now, our goal is to maximize theta. So we need to take the derivative of this equation with respect to theta. So when you take the derivative of this with respect to theta, this part becomes 3 over theta. And when you take the derivative of this part, it's theta times some constant in terms of, when you take the derivative of this with respect to theta, this becomes the derivative of the right-hand side. So in other words, let me just repeat that again. So the derivative of 3 ln theta is equal to 3 divided by theta. It's this term here. And the derivative of theta minus 1, this minus 1 doesn't matter if you multiply minus 1 with a constant. The derivative of a constant term is 0. Therefore, we can ignore this minus 1 part. So theta multiplied by some constant, its derivative will be this constant here. In other words, like the derivative of cx is c. So this is exactly what we see here, the derivative of theta times that constant. So that's the second part. What we do is we set the derivative to 0 and solve the resulting equation. So when we set this to 0, theta hat in maximum likelihood. This is the estimate when we use the maximum likelihood method. All right, we can subscribe this theta hat with maximum likelihood becomes minus 3 divided by this thing. So we just solve this equation. It's very simple actually. We get just we take this to the other side. So this 3 divided by minus 3 divided by this becomes theta. It's just a simple single equation solving, and it simply becomes whatever the logarithm of these xi's. We take the logarithm of 0.4. What were the numbers? 0.4, 0.7, 0.9. We take the logarithm of all these three entities, observations, and we sum them up and we divide. Since all of them were less than 1, they will be negative values. So when we divide this negative 3 with those, we will get some positive number here. So if you can just use calculators for this purpose, and when you do the math, the estimate will be 2.18. So this exercise is a nice exercise in which sometimes method of moments and method of the maximum likelihood method may result in different estimates for the same parameter. They are different methods, all right? But as you can see, they're close. Method of moments gives us 2, but maximum likelihood gives us 2.18. They're estimates, they're approximations, and therefore the result may be different. So this exercise is a good example of how method of moments and maximum likelihood could result in different estimates for the same parameter for the same sample. All right, for the same sample 04, 07, 09, one of them results in 2, the other is 2.18. So this is how we would solve this exercise 9.4. Now I'm going to start talking about exercise 9.5, in which we have like a rather complicated equation here. For example, to solve this problem, I need to actually refer to some I didn't know how to take this complicated integral when we have x times e to the minus x something. So I need to actually look at the Wolfram alpha to figure out what the integral is. All right. So now in this example, we have in this exercise we have again one unknown parameter theta, and so the sample size is 10, and the distribution is from 0 to infinity. It's not bounded as in the previous exercise 9.4. X is from 0 to infinity this time, and this is the probability density function. And what we're given is that the sum of all these 10 observations is given to us. In other words, x bar here is just 15. All right, 150 divided by 10, that's my x bar. That's equal to 15. So again, I can use the first population moment and first sample moment. So this x bar is the first sample moment. And what I need to find here is that find the first population moment. Therefore, I need to figure out what the I need to draw this without taking my hand off. So I need to figure out what the expected value of x is. So this is the first population moment. So we need to compute this. In order to compute that, we need to multiply this PDF with x. All right, I need to multiply it with x and take the integral from 0 to infinity. So this is how you would find this expected value x. All right, that's and it tells us that estimated by the method of moments, so we are going to do that. But the second part, estimate the standard error of your estimator in part A. So that may be a little bit more difficult, but it's not that difficult. In order to estimate the standard error, we need to find the variance of, since the variance of these individual x's are not given to us, we need to also, but we can find that, right? We can actually find also the expected value of x squared. If we find the expected value of x squared, we'll be able to figure out what the variance of, x is with these two things. If you know the expected value of x squared and the expected value of x, by using these two, you can find the variance as an equation. All right, so we will do that actually for part B. So let's take a look at, so I just sketched out the solution for this, and let's see how we proceed. Let's look at the actual solution. It's a 2-page solution because of this integral. So this is the population moment, the expected value of x from 0 to infinity, x of x dx. What we do is the PDF is already given to us. We multiply it with x. So what we have here is x times, so these are constant. 1 over 2 theta is a constant which could be taken out of the integral, x times e to the minus x divided by theta. So we need to use the mathematical knowledge that, so we need to figure out how can we take the integral of something like this, x times e to the minus x divided by some constant dx. So we need to figure out how to take this integral. So I just typed this in Wolfram Alpha. Actually, I used some different constants here, 10, 5, 15, 20, to see what the result looks like. And the result is actually this. If you take this indefinite integral, the result is minus a, whatever your constant is, e to the minus x over a. So this part is just maintained here in the result, multiplied by x plus a. So this, we need to know this information, this integral, in order to solve this question, or actual part A. For part B, I need to know what this x squared is. All right, that I will be using it for finding the expected value of x squared. So that's for part B. Now, by using this, we can write m1. Now, this mu1 now will be written as, since with this mathematical knowledge, I can take the integral now and write it as 1 over 2 theta. That was the constant I took it out from the first term, and 1 over 2 times 1 over 10, which is 1 over 20, is the constant of the second term. Don't remember, we have this multiplicative 2 terms here. So this integral actually is for one of the parts. For the other part, I will be using the same. It has exactly the same form, but with different constants. In one of them, I have theta. In the other one, I have 10. And therefore, the integral is composed of 2 parts here, like this, in which in the first one, I have theta in the first part as the constant, and in the 10 as in the second part. So when we write this thing, the good thing is that these boundaries, 0 and infinity, are really convenient for us, because these e to the something terms will disappear with that. For example, when you have infinity, this part, e to the minus infinity, whatever it is, it will be 0. All right, so 1 over e to the some infinite number, this part will be 0. And since they're all multiplicative, the whole term is going to be 0. Likewise here. So the first term here, when we give infinity, the integral just becomes 0. All right, now therefore, so it's 0 when x is infinity. And the good thing is that when you put x is equal to 0 here, e to the minus 0, that will be 1. So it will be 1 when we give x is equal to 0. So this is exactly what we do. So for the first part, when x is equal to infinity, we get a 0. Then minus, when we put 1 here, it will be, sorry, when we put 0 for x here, 0 plus theta over 2, which becomes minus theta over 2, and this part becomes minus 10 over 2, and we have a minus in front of this thing. In order to compute this integral, we compute the first term minus the second term. So this is that minus second term part. And mu1 turns out to be theta over 2 plus 5. So all these complicated equations at the end result in something really simple. Mu1 is simply theta over 2 plus 5. All right, very easy. And the sample, first sample moment is x bar, which we figured out it was 15. So we equate them to each other. Theta over 2 plus 5 is equal to 15. From here, we find theta is equal to 20. So that's our method of moments estimate for theta. So we figured out the first part. Theta hat is 20. So for this observation, for this sample size of size 10, in which the sum of all 10 observations is equal to 150, our best estimate using method of moments for theta would be 20. All right. Now, what is the standard error of our estimator in part A? So what's the standard? What do we mean by standard error? Okay, so what we mean by standard error is this. So this term is the standard error. What is the standard deviation of our estimate method of moments estimate, which is theta hat? What is the standard deviation of theta hat? So in order to figure this out, we can actually make use of we can write theta hat in terms of, so we figured this out. In order to estimate theta hat, we use this equation in part A, right? Theta divided by 2 plus 5 was x bar. This is what we used here in part A. So we can write theta hat in terms of x bar. It's simply 2 times x bar minus 10. So it's exactly like that. This was 15. 2 times 15, 30, minus 10 was 20. This is how we found out theta hat. Now, this equation tells us that in order to figure out the standard deviation of theta hat, you can actually use the standard deviation of x bar. So this relationship between theta hat and x bar in our estimator tells us that whatever the standard deviation of x bar is, the standard deviation of theta hat, since it is 2 times x bar, the standard deviation will also be 2 times the standard deviation of x bar. So this 2 here comes from this relationship between theta hat and x bar. So this is really critical. And why do we have this 2 exactly as same 2? Because of the linearity of expectation. If you remember, there was a table in chapter 3 which I referred to earlier in previous lectures to figure out the variance between variance of P1 minus P2, for example, is the same as variance of P1 plus variance of P2, because we had this equation there. So variance of some a times x, some constant times x, is equal to a square variance of x. Okay, so in that table we had something like this, variance of x. So which means that the variances of some, so this is 2x, so the variance is going to be 4 times x. So the variance of theta hat will be 4 times variance of x bar. But since standard deviation is the square root of variance, which means that whatever coefficients I have for the variable here, when I take the square root of this a square, so the standard deviation is going to be exactly as the a times the standard deviation square root of variance of x, which is the standard deviation of it. So standard deviations are, they grow linearly as these coefficients in front of it. So if you have theta is equal to 2x bar minus 10, its standard deviation is going to have the exact same relationship as x bar. And what is the standard deviation of x bar? If you know the standard deviation of individual x's, we already know that standard deviation of x bar, when you have the sample size n, is equal to standard deviation of x, individual x's divided by square root of n. Again, this follows from the linearity of expectation, the relationship between variances. So if I know the standard deviation of individual observations, which I label here standard deviation of x, standard deviation of x bar simply is the standard deviation of the averages is actually smaller than the standard deviation of the individual items. The larger the sample size, the smaller standard deviation their averages are going to have, and that's smaller with respect to, that grows very smaller with respect to the size of the sample size, square root of the sample size. All right, so we have figured out the most critical part of part B. The only thing I need to figure it out is what is the standard deviation of individual x's here. In order to find that, as I said on this book here, we need to find the expected value of x squared, because after I find expected value of x squared here, I can use that, and I can also use the expected value of x with that. Okay, I can use the expected value of x as well. By using these two, I can find the variance, and then in turn I can find the standard deviation of the individual item. So for this, in order to find this integral, we need to use the mathematical knowledge that x squared e to the minus x over x divided by a is equal to this. All right, and again, this e to the minus x divided by a is something really convenient for us because it's 0 when x is equal to infinity, and it's equal to 1. This whole term is equal to 1 when x is equal to 0. So simply when we try to figure this out, we see that the same as we figured out the integral here, when we follow the exact same steps, the expected value of x squared turns out to be this term, which is theta squared plus 100. So now I have expected value of x squared in terms of theta squared plus 100. So the variance of individual observations simply as defined, this is how the variance was defined, the expected value of x squared minus the expected value of x squared. So the first part is theta squared plus 100 minus, if you remember, the first sample moment was theta divided by 2 plus 5, this one squared. If you solve this simple quadratic, this polynomial, it turns out 0.75 theta squared minus 5 theta plus 75. So if you just open this up. Now, our estimate for theta was 20. So just plug in 20 here and n in our sample. So the standard error will be, we have the standard error formula at the end of the previous page. All right. So the standard of theta hat is simply 2 times standard deviation of x divided by square root of n. So for this standard deviation of x, we are going to be using our estimate of the variance that by using our estimate here, which is in this case 0.75. So 2 times the square root of, so this was the variance. All right, so this is the variance, therefore I need to take the square root of this one. I'm also taking the square root of n at the bottom, so it simply means that's taking square root of everything. So if you just plug in all the values, there are no unknowns here. N is equal to 10 in our example, and in this case the standard error of theta hat, our estimate, turns out to be 5.24. So this is a rather long exercise, but it's really covers everything about how we compute variance. It covers the sample moments and everything. So I think this exercise 9.5 is going to be really helpful in understanding how we use this estimation method of moments estimation method and what the standard error is. This is also really important. The concepts of standard error is the standard deviation of your estimate. All right, so this concludes exercise 9.5. Now we can continue with 9.7. All right, now let's look at what, yeah, let's just make sure it's 9.7. Yeah, exactly 9.7. So let's read the exercise first. In order to ensure efficient usage of a server, it's necessary to estimate the mean number of concurrent users. So according to records, the average number of concurrent users at 100 randomly selected times is 37.7, with a standard deviation of sigma is equal to 9.2. Now, this sentence actually is rather ambiguous, the second sentence. Actually, this sigma here, when it's given like this, it may mean, I mean, as you can see, the sigma, there is no parameter associated with the sigma. Is it the standard deviation of the average number of concurrent users? Because it could be understood like that easily, right? I mean, according to records, the average number of concurrent users at 100 randomly selected times is 37.7 with a standard deviation of 9.2. So from this sentence, I can understand this 9.2 is the standard deviation of this average. All right. So what I'm saying is that this standard deviation could be the standard deviation of X bar. Or is it the standard deviation of the number of concurrent users at a single time? So the I mean, it could be, because when it's just given as sigma, it may mean a distribution parameter. In that case, it's so X here is our random variable, which means the number of concurrent users at a given time. All right. So X bar is the average of such X's in 100 different observations. So that's what X bar is. So sometimes in the question, I mean, in the exam, when we ask such a thing, we would make it non-ambiguous. I mean, we will make it clear that this is the standard deviation of individual X's or the standard deviation of X bar. But from this question, I understand it's the standard deviation of X bar, which means that actually it's the standard deviation, it's the standard error. All right, so this may be standard error, but since it may be a general convention that when it's given just like sigma with no parameter at all, it's the parameter of this random variable. Therefore, it may be understood as the standard deviation of concurrent users at a given single time. All right. Under these two different interpretations will result in two different answers. All right, I need to be very clear on that. In one case, I will be using 9.2 as the standard error. In the other case, in order to find the standard error, I need to divide this 9.2 by 10. So the actual standard error can be 10 times low, 10-fold smaller than this. It may be 0.92 or 9.2 will give me completely two different confidence intervals. All right, so I will solve the question by both interpretations. So this one says construct a 90% confidence interval for the expectation of the number of concurrent users. So we are going to build a confidence interval around 37.7. So that's our center of our confidence interval. So we need to go a certain number of standard errors to the right and to the left. But what is that standard? The size of the standard error we are going to go. We are going to look at this 90% confidence which is given to us, in which case alpha is equal to 0.1 and alpha is equal to 0.05. So here for part A, all we have to do is look up the z alpha over 2 value, which is z alpha is equal to 0.1 here, and z 0.05 is equal to 1.645. So the confidence interval simply will be 37.7 plus minus 1.645 times standard error. Now that standard error, as I said, is this the standard error is given as 9.2 in the question. This is how I understood from the question, but somebody else can understand that since it's not given like this in the question, just sigma is given. Sigma, when it's just used individually like this, it may mean the standard deviation of the single observations. Is it like the standard deviation? Sorry, standard deviation of X only. All right. In that case, I will have to do something else. In the first case, if 9.2 is interpreted as the standard error, all you need to do is the confidence interval is this x bar plus minus 1645 times 9.2. You just this many standard errors to the left and to the right of your interval, which will give you 9.2 times 16 is something like 15 or something like that. Yeah, it's close to 15. And therefore, you go 15 units to the left, 15 units to the right. It gives you a very large confidence interval, as you can see, because this is a large standard deviation for this number. All right. But if the given standard deviation is the standard deviation of concurrent users at a given time, in other words, is the standard deviation of this individual axis, then we need to build the confidence interval as such, because the standard error in this case will be sigma divided by square root of n, which is square root of 100. There are 100 sampling of 100 observations. In this case, this will be 0.92. And if you multiply it with 1.6, it will be something like 1.5. So you go 1.5 units to the left, 1.5 users to the right. So this becomes the confidence interval at alpha 0.1. All right. I hope this is clear. By the way, if you have any questions about any of these solutions, feel free to email me your questions, and I will try to explain and answer your questions. All right. Now, here now we have a different significance level, 1%. So at which means that at 99% confidence level, do these data provide significant evidence that the mean number of concurrent users is greater than 35? So we have a hypothesis testing in part B. So our hypothesis is that the null hypothesis will be the mean number of concurrent users mu is equal to 35, and we have a right tail test here, because it says that the number of is significantly greater than 35. All right, so what we need to do is form our hypotheses. The null hypothesis is mu0 is equal to 35, and the alternative hypothesis is mu is greater than 35. And we have a one-sided test with this significance level, 0.01 significance alpha is 0.1. We don't divide it by 2 because this is a one-sided test. And the z-value at 0.01, if you look at the normal distribution table, standard normal table, it's equal to 2.326. And the test statistic we are going to conduct is going to be this. We are going to standardize this. The x bar was 37.7, and we have this one is 35 divided by the standard deviation here. If the standard deviation, again, based on the interpretation of whether this 9.2 is the standard error of x bar, or whether 9.2 divided by 10 is, whether this is 9.2 or 0.92, as I said, is going to be different depending on your interpretation of the last sentence of the question. Now, if it becomes, if you interpret it like this, the test statistic, if you interpret it like this, the test statistic is 0.29. In this case, the z is not greater than the value we have here, so we cannot reject h0, because as you can see, 35 is in this you can also take a look at this. We have these, by the way, we cannot use these confidence intervals we used here. Why? Because the significance levels are different. Okay, in part E, the question uses a significance level of 10%. In part E, at part B, 1% significance level is used. All right, so we cannot use our confidence interval is in part A. So we just use the regular hypothesis testing in this case. So we just compare these two values. Since this test statistic we computed here is not larger than this, we cannot reject the null hypothesis. There is no sufficient evidence. But if we interpret this 9.2 as the standard deviation of individual items, then the standard deviation of x bar is equal to 0.92. And if you write it like this, 0.92 here, the test statistic will be 37.7 minus 35 divided by 0.92, and it will be just 10 times larger than this. As you can imagine, it will be 2.935, which is larger than this z value, which means that we can reject H0 when the standard error is 0.92. When standard error is large, we cannot say that there's 37.7 is something significantly larger. But if our estimate, if the standard error is small, which means that we are really confident that the actual number is very close to 37.7, so which means that in that case we have significant evidence that it's larger than 35. Okay, so standard error, the size of the standard error is really critical. So whether we reject or accept the null hypothesis. All right, so I solved this. I hope this didn't confuse you. I mean, these two different interpretations. So there are two alternate answers that I gave, depending on how you interpret this 9.2. If the sigma, as you can see, it's not given clearly, as I understand from the sentence, the average number of concurrent users at 100 randomly selected times is 37.7. With a standard deviation of this, I can associate this standard deviation with the average number. So I can associate it with x bar, which I'm sure most of you may also do. And therefore 9.2 becomes the standard deviation here, the first interpretation. The second interpretation, on the other hand, says that, okay, this with a standard deviation of sigma this sigma, there is no parameter given, so if it's not given, you may also interpret it as the parameter of the random variable, so it's the standard deviation of x. In that case, if it's the standard deviation of individual items, the standard deviation of x bar will be 0.92 in that case, and in that interpretation we get different confidence intervals, and we get different results in our hypothesis test. Okay, so this one was exercise 9.7, and now I'm going to solve two more exercises before I end this video lecture today, 9.16 and 9.17. By the way, Sibel Hoca is also going to solve some exercises from here, especially related to p-values, and I think she is going to solve exercises 8, 10, 11 as well. So Sibel Hoca is also going to solve some other exercises at the end of chapter, which are going to be different than what I'm solving. So you will have lots of exercises solved at the end of this chapter 9. All right, 9.16. It's about proportions, significance levels or confidence levels of proportions. So 9.16, we are actually comparing two different populations and the difference of between two proportions. So there's a sample of size 250 and 10 of them contain defective items, and there's another sample B of size 300 and there are 18 defective items in that sample. The first one is saying construct a 98% confidence interval, so with 2% significance level, construct an interval for the difference of proportions of defective items. So let's call this P1 hat, let's call the other one P2 hat. P1 hat is simply 10 divided by 250 is 0.04. So that's the proportion for sample A. Actually, I could have called them PA and PB instead of P1 and P2. Anyway, so P2 refers to the proportion of sample B. It was 300, 18 of them were defective, and the ratio is 0.06. So as you can see, the ratios are different, 0.04, 0.06. Is this so? The difference between them is, I mean, P1 hat minus P2 hat is minus 0.02. But is it always minus, for example? Can we say, for example, that at this confidence level, P1 is always smaller than P2? So what does our confidence level is our confidence level always, the interval is always negative or not? So let's see. Let's build a confidence interval at 98% confidence level. So alpha is equal to, and also in order to do that, we need to estimate the sample variances. We need to know our standard error in this estimate. The standard error in this estimate is simply given by, this is the variance divided by the sample size. So this one is the estimated sample variance for the first sample, which is the estimated P1 hat times, so this was, if you remember, so this is like a Bernoulli trial, each one of these proportions. So if you remember the variance, it was P times Q, success rate, success probability, unsuccessful probability. We multiply P times Q, that was our variance, and divided by the sample size. This gives us the sample variance for the first sample. So, which means that the standard error of the first estimate here in our sample is square root of this thing. That's my standard error for P1 hat. We do the same thing for the second one by using exactly the same formula with different sizes. So this is the error we could have in such an estimate of size 250, because I mean, if I have collected a different sample size, P1 hat would be different, right? I mean, maybe if I collect some other samples, another 250 samples from the same lot A, I could have get maybe 11, maybe 12, maybe 9, maybe. So this is a random variable. So the standard error of this random variable is simply this entity here, which is P times Q divided by N. Now, the variance of P1 minus P2 hat, which I will be using in building my confidence interval. So in other words, my standard error for the difference of these two things is simply the summation of these two variances. Again, why do we have a minus here and sum these variances up here? Because this is like minus 1 P2 hat, and the variance of some minus x, a variable like this, is equal to minus 1 squared variance of x. So minus 1 squared is equal to 1. Therefore, a variance of minus x simply is equal to a variance of x. And this is also something very intuitive, right? I mean, whether something, imagine you have a variable, for example, the weight of a person. The standard deviation is like, or the variance is like the distance each measurement deviates from the mean, so it's something positive. So if you make the weight something the negative of the weight, the deviation that you measure from the mean, from the negative mean, is going to be exactly the same. So the distance does not matter when you put a negative. Its deviation around the mean does not change when you make the variable negative. So because of this fact, the variance between differences of two variables is simply the summation of their individual variances. Now, with this, the standard error of the difference between, so the standard error of this P1 hat minus P2 hat becomes the square root of this summation. It's 0.01848. So why did I measure this standard error? Because in order to build the confidence interval at a specific confidence level, what I'm going to do is I need to go around my estimate 0.02. Minus 0.02 was the difference between P1 hat and P2 hat, and I need to go around that number a certain number of standard errors. So I need to know my standard error. And how many standard errors I'm going to go left and right, it depends on your confidence level. So if your significance level alpha is 0.02 as given in the question at 98% confidence level, I'm going to divide this alpha by 2, because when you're building confidence levels, they're always two-sided. A confidence interval, sorry, not confidence level, the confidence intervals are always two-sided. You're going left and right to your estimated central value. So when you divide alpha by 2, 0.01, it becomes 2.3. So for this confidence interval, I need to go around this minus 0. So this is minus 0.02, as you can see. I need to go plus and minus this many standard errors to the left and to the right of that value, and it becomes this minus 0.06 plus 0.03. As you can see, although the difference between them is negative, lot A seems to have lower number of proportions. As you can see, this is 0.04, this is 0.06. Can we say lot A always has less number of defective items than lot B? Not at this confidence level, not at 98% confidence level. Our confidence interval contains negative numbers, also it contains positive numbers. What does it say? It tells that sometimes lot A may have more defective items than lot B. If this is my standard error, it tells you that at this confidence level, if you had taken another sample from lot A and lot B, it could have turned out to be a positive number, which means that lot A has more items, or it may be negative. Lot A has less defective items or more defective items. All right. Now, part B is actually related to this because it's asking at the same confidence level. So at a significance level, alpha is 0.02. That significance level is exactly the same as this confidence level. Is there a significant evidence between the quality of the two lots? I would say no, because 0 here is included. So sorry, in this case we have a two-tailed test in which they are different. So are they different or same? So it's not saying lot A is greater than B or lot A has smaller. So it's not a one-tailed test. The test in part B says that is there a significant difference between the quality of the two lots? So our alternative hypothesis is they are different, or their difference is not equal to 0. They are exactly the same things, or the null hypothesis that they are equal is exactly the same as saying that their difference is equal to 0. So since this 0 is included in my confidence interval, it means that it's in the acceptance region. So whatever your hypothesis is here, null hypothesis, if it's in the confidence interval of exact same confidence level, it means that it's in the acceptance region and you cannot reject it. All right. So therefore, without actually conducting any more computations, by just looking at the confidence interval and looking at this difference 0 we are asking in our null hypothesis is included in the confidence interval, we can safely say that we cannot accept the alternative hypothesis. In other words, we cannot reject H0. So we have to accept null hypothesis, saying that P1 is equal to P2. With this confidence level, we cannot say that they are different. All right. So that was the 9.16, and now I'm going to talk about the last exercise that I'm going to talk about today. Now it's again about some percentages, some proportions, and this exercise is also good in the sense that the standard errors cannot directly be added when we're talking about the difference between proportions. So you'll see what I mean in a couple of minutes when we interpret the results of this exercise. So the exercise is like this. So there is a news agency publishes the results of a recent poll, and there are two candidates, candidate A, candidate B. And it reports that candidate A leads candidate B by 10% because 45% of the poll participants supported Miss A, whereas only 35 supported Mr. B. All right, so there are 45% of the people supported Miss A and candidate A, and 35% supported candidate B, and the difference between these two things is 10%. Now, when we're reporting the margin of error, because we should also know that the size of the sample, in which 900 people were used in this survey. So let's take a look at that. What margin of error should be reported for each of the listed estimates? So when we are saying, is that for the 10%, what is the margin? What is the standard error of 10%? The difference between P1 and P2 is 10, all right, 0.1. In other words, in terms of proportions. What is the standard error of this? What is the standard error of this 35? What is the standard error of this 45? All right. This question asks us to compute those. And what will be interesting is that the standard error of 35 and 45, we cannot assume the worst case in both and sum the worst cases to find the worst case of 10%. So you'll see what I mean, as I said in a minute. So and this is asking at 95% confidence interval. Okay, we need to report the margins of error that typically corresponds to 95% confidence interval. So at 95% confidence interval, we have alpha is equal to 0.05, and here n is actually 900. There's a typo there as well. I'm going to correct this before I post this online. So, and when we divide this alpha by 2, we get the z value for 0.025 is 1.96. So 1.96 standard errors to the left and to the right. So the margin of error for the first candidate A, the proportion that was estimated was 0.45. So what we need to do is 0.45 times 0.55, p times q, or p times 1 minus p, divided by square root of n. So when we do that, this is also the variance, therefore we take the square root of everything. So this is the standard deviation of P1 hat. Multiply it with 1.96, you know how much you have to go to the left and to the right of that. So in other words, so it becomes 0.0225. So when these are not percentages but ratios. So when you convert this one to percentage, it becomes, you multiply it by 100, it becomes 3.25. So in other words, when you're reporting this 45% of the population supports candidate A, actually we need to say that 45 plus minus 3.25% support candidate A in the population at 95% confidence level. So this is actually how it should be reported. If you at 95% confidence, our guess of 45% could be off as much as 3.25%. So it could be 48.25, or it could be 42.75. All right, or no, 41.75. Okay, so 45 minus 3.25, whatever that number is. Okay, we do the exact same thing. So this is the margin of error. 3.25% is the margin of error for candidate A. We do the same thing for candidate B. 0.35 multiplied by 665 divided by the same number of samples. And in this case, our estimate could be wrong with 3.12% values. So 35, when we're reporting this, 35 could be 38.12 at most, or it could be as small as 31.88, all right, at 95% confidence level. So this is plus our margin of error is 3.12 for this. Now, if we look at these two things, our margin of error could be, for example, if this is as low as it can be, 31 point something, this is as high as it can be, 48 point something, the difference between them actually is going to be like 16 something, right? I mean, their original difference is already 10. So it could be 48, this could be 31, so it could be as large as close to 16, 17. So is it like that? Now let's look at the margin of error for the difference. So the margin of error for P1 minus P2, that estimate the difference of proportion is 0.1 as reported originally in the news article. Now at 95% confidence level, what is the margin of error for this? What are we going to report in terms of 10%? Can it be as large as 16%? Can it be as low as 5%? What is it? Okay, so in order to do that, I need to know the standard error for the difference. The standard error for the difference is computed like this. It's not I find the standard deviations of the individuals, I add them up. So these were the standard error of the individuals, and their square root is equal to the standard error of the difference, which turns out to be 0.045. So in other words, in terms of percentage, it's 4.5 actually. A 10% difference is actually should be reported as 10 plus minus 4.5. It cannot be as large as 10 as sorry, it cannot be as large as 6 as we have reported here. It's actually at 95% confidence level. It's a value that ranges between 14.5% and 5.5%. So the difference that we are reporting, the confidence interval actually is 5.5%. It's somewhere between 5.5% and 14.5% at 95% confidence level. All right, so this is how we would report the difference between these two candidates. All right, this concludes the exercises that I'm going to solve at the end of chapter 9. As I said, I'm going to solve some other exercises at the end of chapter 10. On Thursday, I'm going to post another video on those exercises. All right, that's it for this video lecture. Take care. Best wishes to everybody. Bye.